Hello friends, we are going to learn the concepts of machine learning in this series like linear regression, logistic regression, decision tree, naive-based neural network. We won't go to discuss the very complicated formulas in this series. We are going to discuss the fundamental concepts and we'll also do hands-on exercises using Jupyter Notebook, Python, Scikit-Learn and Pandas. If you want to know in detail, you can join my course. I'll give the link in the description box. Today, we are going to learn linear regression. We are going to discuss the very first topic in machine learning, the concept of linear regression with single feature. Our objective today is to understand very basic and fundamental concept of linear regression without going into the depth of very complicated formulas and all. At the end, we'll write a simple code in Python to see how it works. To understand the intuition, let's see the formula. It's a very simple formula to convert the temperature from degree Celsius to degree Fahrenheit. Super simple. So if we just write a very simple program, we can populate the data as we can see in this picture. Now let's think the other way around. Say for example, we have this data and just by looking at the data, we can say if there is any correlation between the first column and the second column. Okay? But if we study in detail and plot the data, probably we'll be able to find there is some relationship. Okay? And that's the objective of linear regression and in a broader term for machine learning also, to find the relationship between the variables and the results in the data set. Okay? So here we are trying to find what is the formula to arrive at this data set. Let's take another example of a very small data set showing the area of office space in square feet versus the price in INR. Just by looking at the data, we can say whether there is any relationship between the area and the price. Okay? In fact, in real life, there are numerous factors that play a vital role in determining the price, like whether it's furnished or not, what is the locality, what are the other facilities, etc. But for the simplicity's sake, let's plot the data and let's find that there is some pattern over here. So from this pattern, can we say or can we derive a formula where we fit the area and get the price? If we can do that, that is what is called the model. So in linear regression, we'll try to fit a straight line that we call as hypothesis. But which line is the correct line or the best line? A line can be drawn like this. Okay, so let's call it hypothesis 1. Or a line can be drawn like this. Let's call it hypothesis 2. But at this moment, we don't know which is the best line. So our objective is to draw the best fitting line with these points. So these are the points and we have to find the best fitting line. And let's say here our hypothesis is hx equal to w0 plus w1x. And if we remember the straight line equation in coordinate geometry, it's like y equal to b plus mx, y equal to plus mx, where b is the intercept, and m is the slope. So here this w0 works as the intercept and w1 works as the slope. Now to find the best fitting line, we can have various straight lines. Let's see. And in this picture, the straight lines are drawn with the same w1, that means same slope but different intercepts w0. So there can be possibilities of various lines like this. Or there is another possibility, that same w0, that is same intercept with various w1 or various slopes. So actually we will have a combination of both multiple W0s and multiple W1s. Okay? And from there, we'll find the best fitting line. Now let's draw the first line. This line might go through some points, but many points will be away from this line. So the points those are away from this line are actually deviations. The ideal case would have been all the points are falling on this line, but in reality it's not so. So we have to find the deviation. So say for example, here is the deviation, right here is the deviation. Now let's take this particular point. This is hypothesis X, and this one is the Y, which is the actual point, and this is the deviation in between. We have to find this deviation, that is Hx minus Y, that is the deviation. So we are also calling it as error I. I means the ith example. So there are 7 training examples over here. This is I equal to 1. Okay. And this is, say for example, I equal to 2. This is I equal to 3. I equal to 4, something like that. Okay. So error I, that is Hxi minus Yi. So that is the error from one of the points. So that way we have to calculate the errors from all the points, and since there could be some negative and there could be some positives, then we have to square all the deviations or square all the errors and add those errors. Okay, so from I equal to 1 to m, so for all the points we are adding the squares of these deviations or the errors and then take the mean. So that is called the mean square error. And what we are doing, we are also multiplying this whole thing by half. In essence, it comes as 1 by 2m summation I equal to 1 to m hxi minus yi whole square. Okay, so that is the mean square error. So why are we multiplying this by the half? Because when we'll see later that when we differentiate to minimize this one, so this 2 will cancel with these 2. So that's the reason it's called an convenience factor. So now that we have come to know as the mean square error. Okay, now let's go to the next slide and see that this mean square error is actually called the cost function in terms of machine learning terminology. And cost function, which is also called as J, cost function J depends on values of W0 and W1, intercepts and the slope. So these are the two factors over here, W0 and W1. The cost function depends on these two factors, and the cost function is written as J of W0 W1 equal to 1 by 2m summation I equal to 1 to m hx minus ys. So mean square error is actually the cost function. And what is the objective? Objective is to choose W0 and W1 in such a way that J is minimized. Now we'll do some calculations and see how it works. Now we are doing some manual calculations and taking simultaneous values of W0 and W1, different sets and different combinations of W0 and W1. And as you can see, say for example, we are taking W0 as 1 and W1 as 1.1. Okay. And this is our X values, and this is the price or the Y values, and this is our hypothesis. Based on this W0 and W1, W0 equal to 1 and W1 equal to 1.1. So based on these W0 and W1 and X, we calculate the Hx. And then we calculate the error. Error means Hx minus Y. So that is the error. Okay. For each of these points, we calculate the error, and then we square these errors so that there is no negative signs over here. And we add these errors. That is a summation. So that is the sum of error square, and we divide it by 2m and get the J. this particular J or cost function is for one combination of W0 and W1. Now we go for other combinations of W0 and W1. Say for example, W0 is equal to -1 and W1 equal to 1.4. So here we find that the cost function is 12.41. Earlier it was 15.23. Let's take another combination. W0 equal to 6 and W1 equal to 1.1. So here we find cost function is 7.95. And there is another combination for W0 equal to 5 and W1 equal to 1.2, and we can find another cost function that is 8.72. So among all these, and there will be numerous such calculations like that, so we cannot show all the calculations over here. And if we try to take a snapshot of all those pictures, then we can find that for different W1s and W0s, we can find these cost functions. So for example, for all W1 equal to 1 and W0 equal to say -2, -1, 0 up to 8, there are several cost functions. And from this batch, you can find that the minimum is 7.7. And then we take W1 as 1.1 and the same combinations of W0 from -2 to 8. And then W1 equal to 1.2, W1 equal to 1.3, W1 equal to 1.4. For different sets of values of W1 and W0, we find that there are some variations of these cost functions. And if we now take, so how do we know that what is the lowest possible or what is the minimum J value over here? So we have to make a 3D plot from here. So we go to the next page and see that on this axis we have W0, and on this axis we have W1s. Okay, and on the vertical axis we have cost function equal to J. Now see, this is an interesting picture. For each of these W0s, when W0 is say 6 and W1 equal to 1, so we find this point. And what is the cost function over here? That is 7.7. That is the vertical line. And for W0 equal to 5 and W1 equal to 1.1, so we find this point and the cost function as 7.4. So actually we have to plot all the points over here, W0 and W1, and the corresponding calculated value of J. And if we can plot, we can find actually from there what is minimum calculated value of J or the cost function. And for that combination of W0 and W1 for which this J value is minimum, that is the best. So in this case, this one and this one. Okay, so that is the best fitting line for our hypothesis Hx equal to W0 plus W1x. Okay, so that was there. So for that combination of W0 and W1, like W0 equal to 5 and W1 equal to 1.1, we get the best fitting line. The question is this the way to find W0 and W1? No. We have a method called gradient descent to find the lowest possible value or the minimum value of J. That we'll learn in our next class. But overall, this is the intuition of linear regression with single variable. What is the single variable or the single feature over here? That is the area of the office space. Okay, so based on area of the office space, we are finding the price. So that is the linear regression with single feature. So if we have multiple features like values for locality, values for whether it is furnished or not, whether it is a new building or the old building. So if we have all the values of those features, we can have a better prediction of price. So that is called linear regression with multiple features. We'll just go for a small Python program using Pandas and Scikit-Learn to see how this works. Now we're going to write a small code in Python using Pandas, Matplotlib and Scikit-Learn to see how the model is built and how we do. Just to save time, I have typed out all the codes over here. So we'll just explain and run and to see how it works. So what we are importing different libraries over here, importing Pandas as PD and importing matplotlib.pyplot as PLT. Okay. And this is from Scikit-Learn, from Scikit-Learn import linear model. So these are the libraries that we are importing. And I have already created the CSV file, the example that we had shown earlier with this data, that office space xy.csv, where on the x side we are having the office space areas in 100 square feet, and on the y side we have the price in million INR. Okay. And we are storing this in the data frame df just to see. Yes. So here, say for example, 5 means 500 square feet and the price is 15 million. Now we are just plotting this to see how the data look. On the x side, that is the office space, the level is office space in 100 square feet. On the y side, the level is the price in million INR, and it's a scatter plot with the x and the y. The color is the purple and the marker as a dot. Okay, so this is how the scatter plot looks like. And now we are building the model. So we have already imported this linear model, and from this linear model dot linear regression, we are creating the model object. And then we feed the data, the df_px and df_py, feed the data to the model. Basically, we are training the model over here. Now, based on this, the model is created, and now the model is returning the two things. One is the intercept, other one is the coefficient. Intercept is W0, this is the weight as W0, and coefficient as the W1. This is the slope that we are saying. Now, the coefficient is in terms of array. Why? Because if it is a single feature, then there is only one value in the array, and if there are multiple features, there are multiple values in the array. So that is W0 is equal to 5.066 and W1 is equal to 1.091. We have seen that already in our example, that W05 and W1 1.1 give the lowest value of cost function in the manual calculations, and this is the calculations that we are getting from the model. Now we are trying to put the line in the scatter plot and see how the line goes. So these things are same as the x level and the y level and the scatter plot, and here we are just drawing this line. So plt.plot is the x side and the y side is the equation of the line, that is W0 plus W1x. What is W0? That is model.intercept underscore, and W1 is a model.coefficient underscore. Now if we plot this, you can find that at this line. So this is the best fitting line or the model that is coming out of this data set. If we have to predict from the model, we have to use model.predict as shown here. We have seen linear regression with single feature. For complex models, we'll have to use linear regression with multiple feature or even polynomials. We'll learn that in our subsequent classes. For today, thank you very much.